So, in the last lecture we started our discussion on the MIPS 32 instruction set architecture, a small subset of it, and was talking about the instructions that we are actually going to implement as part of these lectures. Now, in the present lecture we shall try to see what are the steps involved in instruction execution. We shall not be talking about pipelining now, we shall be looking into pipelining later. Right now you forget pipelining, but what we are trying to understand and learn is that for any instruction, it can be add, it can be load, it can be branch, what are the steps that need to be carried out inside the processor so as to execute or fulfill the functionality what is actually required of the instruction. Okay. So, this is our part 2 of the discussion on this. Okay. Let us come straight to a breakup of the instruction cycle. Now, talking about an instruction cycle refers to a time period that is required for the execution of a complete instruction. Now, here we are saying because the processor or the instruction set that we are trying to design and implement is very simple, this instruction cycle can be very regularly divided into 5 different, you can say, sub cycles or steps. Okay. So, what we are saying is that the total instruction execution cycle we divide into these 5 steps. So, what are these 5 steps? First step is called instruction fetch. So, here we are fetching an instruction from the memory. So, we know that the program counter, the PC register already contains the address of the next instruction. So, simply whatever is there in PC, from that memory location we read, that is instruction fetch. Then second step is instruction decode. Here we are trying to decode the opcode and find out what kind of instruction it is add, subtract, multiply or what. And in parallel, while decoding is going on, as I had said, we also do some register prefetching. Well, assuming that the instruction will be requiring both source registers, we will be prefetching the registers. Not only that, assuming that there will be a 16-bit immediate data, we will take that last 16-bit of that instruction and we will be doing a sign extension to 32 bits. These things we are doing in anticipation. We really do not know whether these things will actually be required or not. It will be known only after decoding of the instruction is complete. And the third step is execution, where actually an arithmetic logic unit is used. Here we execute the instruction, or for some instructions we have to compute the effective address. Well, you think of a load instruction. The load instruction that we talked about was like this: load, let us say R5, 56, R12. So, the value of 56 and R12, they will be added and the result of the addition will be your memory address, from where the data will be loaded into R5. So, you see you require an addition step here. Okay. In the load instruction, no other arithmetic calculation is required, only this addition to compute the effective address or the operand address. So, that is what is mentioned here. In the EX stage, for such load and store instructions, we can also do the effective address calculation. Then in MEM, we can actually do the memory access, read and write from memory, and also for branch instruction, we can also decide whether to branch or not. And the last stage, WB, it is register write back. Let us say I have an add R1, R2, R3 instruction. So, R2 and R3 will be added, result will be stored in R1. So, the result stored in R1, this will be taking place in the WB stage, last stage. WB stands for write back, register write back. And the different steps that are going on, even within each of these steps there are several sub steps. These are called micro instructions or micro operations. We shall be showing you what are the micro operations that are required in the different steps. You will be able to understand. Let us start with instruction fetch. Here I have said that the instruction pointed to by PC, PC always contains the address of the next instruction to be executed. So, whatever PC contains, you fetch that word from memory and store it in an internal register. It is called an instruction register, we will see it later, but this fetch is going on. And we are assuming, this already I mentioned earlier, that every instruction is 32 bits long. Also every memory word is 32 bits and has a unique address, so that after an instruction has been fetched, you will have to increase PC by 1 to point it to the next instruction. So what you do, this is the instruction fetch, mem of PC, this is memory, just like accessing array, something similar to that. You are accessing memory whose address is in PC and you are storing into a register called IR. This IR stands for instruction register, okay? And you increase the PC and do not store it back in PC, because for jump instruction the target address can be something else, you do not know it yet. So, you use another register called new PC, NPC, store it temporarily in NPC. This is what we do during the instruction fetch stage, right. Now, just one thing, for some memory systems the memory words are byte oriented, means every byte has a unique address. So, if we talk about 32 bit instructions, so we will have to increase PC by 4 to go to the next instruction, because there are 4 bytes in every instruction. But for our example, we are considering word addressable to keep it simple, okay. Fine. Next, let us come to instruction decode. Now, we have seen that the instruction format is very regular. The opcode is always in the first 6 bits, bit number 26 to 31. The first source operand, so the wherever is there, will be in bit number 21 to 25, and the second source operand in bit number 16 to 20. 16 bit immediate data 0 to 15 and 26 immediate data for jump instruction, we are not using this, so ignore this for the timing. So, decoding and register prefetching RS and RT will go on in parallel. Similarly, immediate data will be sign extended. Let us see what happens. These are the micro operations. We are doing register prefetch, you see the two fields are RS and RT, right. So, we are writing it like this, reg RS, reg RT. We are fetching the register, there are 2 read ports. So, in the earlier examples of register bank we saw, you recall, we assume that there are 2 read ports and 1 write port. Now, we can correlate why we need that. You see here we are reading 2 things at the same time in the same cycle, right. So, 2 registers are fetched, one you store in A, other you store in B. And this is how sign extension is carried out. Okay, the last one you can ignore because this we are not implementing. Let us try to understand what we are doing here. See, you see we have a 16 bit immediate field, we have to extend it to 32 bit. So, what we are doing is as follows. So, we have a 16 bit immediate field. Now, this 16 bit immediate field is considered to be a signed number in 2's complement. This is how it is regarded, 2's complement signed number. So, if the number is positive, it will start with 0, 0 then anything. If the number is negative, it starts with 1, then anything. Now, sign extension means we want to extend this number to 32 bits, to make it 32 bits. Now, in 2's complement, the rule for sign extension is very easy. It says whatever is the sign bit, you replicate that. If the number is positive, just add 16 zeros in the beginning. That will make you make the same number in 32 bits. For negative number, similarly, if the sign is 1, you replicate this first 16 bits with 1, the value remains the same. Okay. So, sign extension means just this, you replicate the sign bit 16 times, right. Now, this we are representing it like this notationally. You see IR, the last 16 bits I am writing as 0 to 15 like this, and this 15th bit IR 15 is the sign bit. This we are replicating it 16 times, to the power 16 means is just a notation, 16 times replication, and this double hash means concatenation. Well, of course, when you write in Verilog, we have some other ways of representing. There are those curly brackets, concatenation operation, replication operation, those are there. But this is a symbolic notation, not in Verilog. I am just writing it in symbolic notation. And this A, B, IM, etc., these are all temporary registers which will be required later. Then comes the execution step, EX. Here we either execute the arithmetic and logic operation whatever is asked for, or we calculate the effective address for load and store instructions. Basically, in this step the ALU is carrying out some operation. Now, exact operation will of course depend on the instruction, and the operation will be carried out on numbers which are already generated by the previous stage A, B, IMM. So, it will be operating on these numbers A, B, IMM, etc. Let us see, depending on the type of the instruction, how the steps in the EX stage can vary. Well, if it is a memory reference, there will be load and store instructions. So, I have shown an example of a load. Here we calculate the effective address in this step. You see A will contain the value of R8, this is the source register, and IMM will consist of this immediate data. So, A plus IMM, this R8 plus 100 is calculated, and the effective address is temporarily stored in a register called ALU out. Similarly, for register ALU operation like this, let us say subtract R2, R5, R12, here A is R5 and B is R12, and func is actually the kind of the function, subtract means this is subtraction. So, you actually carry out the operation specified by the instruction on the operands which will be in A and B, and again this store the result is stored in ALU out. And if it is an immediate operand, there is immediate operand, register immediate, then it is similar to this, but the second operation is not B, second operand will be IMM, R5 will be A and 524 is IMM. Okay. And for branch, you do these things. Here the label of whatever is the offset, that will be the last 16 bits, that will be your IMM, that will be added to NPC. Okay. Because you still now do not know whether you are taking the branch or not taking the branch, but in case you take the branch, where to go, you are making that ready. You are adding the program counter, that NPC, with this offset and getting ready with the new address in case you decide later that well I have to take a branch. Okay. And also you calculate the condition, because there is branch equal to 0, you check whether A R2 is A equal to 0 or not, and that result of this comparison you store in a flip flop, a 1-bit register called cond. This will be required or used in the next stage. Now come to the mem. Mem, here we do memory access or branch completion. So, only load, store and branches they use this stage, other instructions they do not do anything in mem. Let us see what is being done. For the load instruction, you simply do this because in load instruction the PC will be the NPC. So, just the NPC you load into PC and you do a memory read, because in the previous stage already the address of the operand is stored in ALU out. So, you access memory with that address and the data that is coming out you temporarily store in a register LMD, load memory data. Okay. This is also temporary register. For store instruction it is just the reverse. Well, first thing is again NPC goes to PC and B, whatever is there in B, that you store in mem ALU out. This is what you do, because for a store instruction your B is the target, right, second operand is the target, that will be stored here ALU out. And for branch instruction in the earlier stage you have already computed cond. So, now you check if cond is 1, then there is a branch. So, the new value of address you have calculated, that goes to PC, or otherwise this NPC, just the next instruction plus 1, that goes to PC. This is what is done during the mem stage. And for all other instruction just you copy NPC to PC. Lastly, in the WB stage you have to write back the register to store the result. Result is written back into the register. Now, the result that you are writing back, it can either come from the memory like a subtract, add, multiply instruction, or it can be load instruction where the data is coming from memory, because you see earlier the data from the memory is coming into a register called LMD. So, from LMD it will go, right. Now, one thing you see, for a R type instruction your destination is RD from bit number 11 to 15, and I type instruction your destination is RT bit number 16 to 20. So, depending on the type of the instruction you will have to decide on the destination register, right. So, let us see. If it is a register ALU instruction, that means this one, first one. So, RD will be your register target. So, ALU out will be stored in reg RD, but if it is a register immediate it will be stored in reg RT, because RT is the target. Similarly, for a load instruction the data is stored in LMD temporarily, that data will be loaded into reg RT. Okay. So, this you have to remember, use RD here and RT here. Now, let us look at some instruction execution in completion, complete set of micro operations. So, if you look at this you will understand what is happening. Take this instruction, add R2, R5, R10. So, R5 and R10 is added, result is stored in R2. Let us see in the 5 stages what is happening. For IF you are fetching this instruction in IR and incrementing PC, that goes to NPC. Second stage, well, IMM I am not showing because this instruction does not require IMM, it only requires reg RS and reg RT. So, they are stored in A and B. So, in the EX stage it will decode, it is an add. So, there will be an addition operation, A plus B will be carried out, result will be stored in ALU out. Mem, nothing other than NPC goes to PC, this copying, nothing else is done. And in the write back, whatever ALU out is computed, that will finally be written to the register RD, RD is R2, right. So, in this way this instruction gets executed, these are the steps. Let us take another example. This is an immediate, add immediate instruction, okay. There is an immediate operand here. So, instruction fetch is identical. So, fetch an instruction, increment the PC. Here there is only one source operand R5. So, I am not showing B, I am only showing A. The relevant ones I am only showing. A equal to reg RS, this is RS, and immediate data is 150. So, in IMM this 150 gets sign extended, you store in IMM. In EX, you add A and IMM. So, R5 and 150 gets added. MEM same, NPC goes to PC, and WB similar, but instead of RD here it goes to RT, because in this instruction format only 2 registers are specified, RS and RT. Fine. Let us look at a load instruction. Load R2 200 R6. So, here this 200 will be added to R6 to get the memory address from where data will be loaded into R2. So, IF is again same as in the early instructions. This ID is also same as in add immediate. The first operand R6 is loaded in A and the immediate data 200 is loaded and sign extended in IMM. In EX, for load and store instruction, this will always be add. So, this 200 and R6 are added, result in ALU out, and in MEM, well, other than NPC to PC, another thing is actually done, that means memory access. This ALU out actually contains the memory address. MEM of that is read and the data gets stored in LMD. And lastly, in WB, that LMD is written into register RT, here RT is R2. Okay. Now, lastly, let us look at a stored instruction. It will be quite similar, but in stored instruction you see in the last step there is nothing to do. First step IF is again identical. Well, in ID, well, here you are actually loading RS and RT both, R3 and R10. It depends on the implementation. This is just one implementation I am showing. Now, in our actual implementation will make it a little different. So, let us say the first one is R3 is RS, R10 is RT, let us say. That is the convention I have shown here in this. This ALU out A plus M same way, you compute the address, and here you write B contains this R3. So, B will actually get stored in R10 is A, R3 is B. So, when you say store, this B will get stored into the memory, right, and this store operation is complete within MEM. So, in WB you do not have anything to do. So, this is a gap. And one example of a branch instruction, branch equal to 0, it checks whether R3 is 0 or not. If it is 0, then it jumps to level. You see what is done here? Instruction fetch is again same, instruction decode, R3 is fetched into A, and immediate whatever offset is there, that is sign extended in IMM. In EX stage, you are adding R3 with this, not R3 this, sorry, you are just adding the program counter, the NPC with the offset to compute the branch address in case you decide to branch later. Okay. So, you are adding these two up, and also you are checking the branch condition, because the branch condition was equal to 0. You check this R3 is already loaded in A, you check whether A is equal to 0 or not, just a comparator, and the result of the comparison you store in this flip flop 1 bit register cont. In MEM you check this cont. Okay, NPC PC is of course the first thing that you do, but you may have to override it. If cont, your ALU out goes to PC. Okay. So, here you can also write it like this, if cont PC equal to ALU out, else PC equal to NPC, you can also write like that. WB again there is nothing for branch. Okay. Now, you see whatever we have talked about, just overall the data path can be very conveniently represented or drawn like this. This is our non-pipelined data path of the MIPS 32. You can identify the different stages. You see here this is the instruction fetch, where this is the memory which stores the instruction, PC is the address, and you read the memory, the instruction is read out, you store it in the instruction register IR, and there is also an operation NPC equal to PC plus 1. So, there is an adder that adds 1 to PC and result stores into NPC. So, this is your instruction fetch. Now, in instruction decode, of course, the decoder is not shown. So, in the IR, that opcode part of IR is decoded, and the RS and RT part, the two source registers, they are prefetched. One of them is loaded in A, another is loaded in B, and the last 16 bit offset, that is sign extended, that is stored in IMM. In the EX stage, you operate on two numbers. Well, of course, the function will depend on the instruction type, I am not showing that, whether it is add, subtract, multiply, what, but the data that you are operating on, that can be different. The first data can either be A or NPC. NPC will be for the branch instruction, recall, because NPC will be added to something. So, it can be either NPC or it will be A. The second multiplex will be selecting B or the immediate data. This also depends on the instruction, and the ALU stores the result in ALU out. And in the EX stage, I said also you have a comparator which checks whether A equal to 0 or not, and the result is stored in a 1 bit register cond. In the MEM stage, you actually do either a read or a write. So, the memory address is obtained from ALU out, and in case you want to do a write, the data is in B, B is written here, and in case you do a read, the data read will go to LMD, and this is the write back stage WB. Well, see, WB is nothing extra, just there is a multiplexer which writes back something into the register bank, because register bank is already here. There is a third write port, okay, using RD. So, RD is already known, that means what was the destination register, and the data can be either coming from LMD for load instruction or from ALU instruction, it will come from ALU out. That data will be stored in register. So, you see, this is the overall architectural execution process of the MIPS. Now, because the instruction set was so simple, because the instruction encoding and decoding is so simple, you see the whole data path I can fit in a single slide. But you think of a more complex processor, is it possible to do this? No, no, you cannot, you can never do this for a more complex instruction set. So, for the RISC or reduced instruction set computer, this is the main advantage. Implementation becomes very, very simple. Okay. So, this architecture which I have shown so far, the data path for a non-pipeline case, in the next lecture we shall be showing how this can be partitioned into well defined pipelines, what will be the stages, and how we have to modify the micro operations to suit the pipelining requirements. Okay. So, with this we come to the end of this lecture. We shall be looking at how to extend this data path to a pipeline data path in our next lecture. Thank you.